Good morning, everyone, and welcome to virtual seminars in Precambrian geology. It's my honor to introduce Dr. Alexie Millikin, a postdoctoral research in the Department of Geological Sciences at the University of Colorado Boulder. Dr. Millikin completed her PhD at Yale University, where she focused on the timing, tempo, and drivers of Proterozoic environmental change. Alexie's work spans radiogenic isotope geochemistry, stratigraphy, paleomagnetism, geochronology, and sedimentary geochemistry, with fieldwork ranging from Svalbard to Namibia to Mongolia. On a personal note, she's a great lab mate. We're fortunate enough to have her here at CU, and today we're fortunate to have her with us at VSPG. Please join me in welcoming Dr. Alexie Millikin. Please take it away.
Great. Thanks, Jim. So today I'm going to be talking about a portion of my PhD work, and that's on the geochemistry of Neoproterozoic strata from northeastern Svalbard, and specifically how they can be used to reevaluate the prevalence of basalt weathering during the Neoproterozoic. So I want to start off by acknowledging that the work I'm presenting today, especially all the field work, was done very collaboratively with all of the wonderful co-authors I've listed here and a number of other field assistants, and of course, a number of funding sources that made this field work and lab work possible. So just to orient you all, Svalbard is located up here in the Arctic Circle north of Norway. And as you can see in this photo here, this geologically recently deglaciated fjord provides really excellent outcrop of this Neoproterozoic strata. So these are vertically dipping beds here. And today I'm going to be focusing on Neoproterozoic strata from the eastern basement province of Svalbard, which is in yellow here. And the sedimentary succession, which I'm showing schematically here on the left, shows that the sedimentary units unconformably overlie Mesoproterozoic sediments, as well as the Kaphanstein group. So those are intrusive and volcanic units that are early Tonian in age. So you can see the Neoproterozoic timescale along the far left here. And these sediments are interpreted to record sedimentation outboard of Laurentia in the Neoproterozoic. So the lowermost unit, the Veteranen Group, represents long-lived deltaic and storm-influenced marine sedimentation with potential fluvial deposits in some of these larger sandstone bodies. The Veteranen Group is about 4 kilometers thick, and it's composed dominantly of shallow marine siliciclastic sediments with some occasional subaerial exposure. So I'm showing here just some examples of the really beautiful clastic sedimentary structures recorded in these units. And then at the top, we have a gradual transition to the overlying Akademikerbreen Group, which marks the establishment of a carbonate platform and is also thought to represent the onset of thermal subsidence in this basin. The Akademikerbreen Group itself records long-lived shallow marine carbonate sedimentation. There are a variety of facies, including really beautiful microbially influenced sedimentation. So on the top here, I'm showing some large-scale bioherms. On the bottom, you can see some beautiful stromatolites. And then moving up into the Polarisbreen Group, this hosts 2 distinct glacial diamictites that have been correlated with the Sturtian and the Marinoan snowball earth glaciations. On the bottom here, I'm showing a photo of the older Petrovbreen diamictite. This one is thinner, maybe up to 50 meters thick. It's a massively bedded diamictite dominated by local carbonate class, and that is interpreted to have been deposited in a marine environment. And then on the top here is a cliff face view of the younger Wilsonbreen diamictite that's overlain by the Dracoesan Formation. And the Dracoesan contains a typical post-glacial cap carbonate sequence that includes distinctive sedimentological features that we typically see in this Marinoan deglaciation. The Wilsonbreen Formation is much thicker, up to around 130 meters thick, has a much wider variety of extrabasinal class and also more varied facies, including sandstones and actually synglacial lacustrine carbonates. So together, these strata, especially the more heavily studied Akademikerbreen and Polarisbreen groups, have been really integral to our understanding of Neoproterozoic Earth history. These diamictites and cap carbonates of the Polarisbreen group were studied starting in, or as early as the 50s and 60s by Harlan and Wilson, and provided some of the early evidence for widespread low latitude glaciation. And then the Akademikerbreen Group has provided a lot of insights into taphonomy and the complexity of Neoproterozoic ecosystems since the 80s and 90s, when the sedimentology and paleontology of these units was extensively described by Andy Knoll, Nick Butterfield, Ian Fairchild, and many others. The carbonate sedimentology of the Akademikerbreen Group has also been heavily studied, recording a number of interesting sedimentological features like sedimentary talc, abundant giant ooids, primary marine cements, and also recording a number of negative carbon isotope excursions. So in the Svanbergfjellet and Grusiebreen formations, we record the Bitter Springs carbon isotope excursion from around 810 million years ago. Oops. And then below the Sturtian diamictite is the Versoia member, which records a negative carbon isotope excursion, which I'm plotting the data for here in purple. And that's now been correlated with carbon isotope records from Ethiopia and Northwest Canada based on a new radiometric age that we published back in 2022. And an important outcome of this work is that there's a 10 to 15 million year gap in the sedimentary record below the Sturtian glacial deposits in Svalbard, and indeed in a lot of other locations globally. But despite that unconformity, the rest of this Tonian record in Svalbard is really continuous, and it can provide a lot of good insights into the Tonian environments and climate state that preceded snowball earth glaciations, and into other geologic events like the impacts of the breakup of the supercontinent Rodinia, the mechanisms behind and significance of these negative carbon isotope excursions, as well as major changes occurring in the biosphere with the ongoing diversification of eukaryotes. But despite this potential, the lower Veteranen Group has remained largely unstudied. The sedimentology and stratigraphy framework was only recently published by Gibson et al. In 2021, which is part of this larger effort that I'll be talking about today to characterize these units. So I'm really only going to talk about a portion of this, largely focusing on the shale geochemistry and provenance of all of these units. But I want to note that with detailed stratigraphic sections and carbon and oxygen isotopes, we were able to take this really massive amount of data we collected and integrate it with previous work done in Svalbard and with global correlations. And today I'm going to be focusing on how these empirical records from Svalbard provide insight into one of the biggest remaining questions about this Neoproterozoic glaciation, and that is what caused them. Not only is this the most extreme climate change in all of Earth history, but also the Neoproterozoic glaciations occurred after about 1.5 billion years with no record of even high latitude glaciation in the rock record. So understanding what caused these glaciations can provide insight into the combination of factors that together made Earth susceptible to global glaciation at this specific time, and more broadly will help to understand the processes that govern Earth's climate state. So the breakup of the supercontinent Rodinia and emplacement of a number of large igneous provinces, or lips, just before the onset of the Sturtian glaciation has led many workers to suggest a causal mechanism between the two. So here on the bottom, I'm showing a paleogeographic reconstruction of the extent of Tonian large igneous provinces and a timeline of their eruption or emplacement at the top. And the fire and ice hypothesis which was originally proposed in 2003, is this idea that having all of this highly weatherable basaltic material in the warm, wet tropics would have increased planetary weatherability, or the planet's ability to turn atmospheric CO2 into alkalinity via silicate weathering and sequester it, and would thus cool the climate. And recent geochronology suggests that the Franklin Large Igneous Province was emplaced about 1 to 2 million years before the onset of Sturtian glaciation. This is some work previously presented in VSBG. And this 1 to 2 million year duration between the emplacement of the Franklin and the onset of glaciation is a viable duration for the drawdown of CO2 via silicate weathering to cause cooling and glaciation. I think this is illustrated well in this figure by McDonald and Swanson-Heisel, that Franklin Large Igneous Province emplacement would have been accompanied by a flux of CO2 via volcanic degassing, so higher on the y-axis, and then that would be balanced by a higher sink, shown by this higher slope here, due to increased weatherability of the Franklin basaltic material. And then within a few million years, CO2 would have actually stabilized at a lower concentration, so to the left on this x-axis, and that's due to decreased weatherability as regolith begins to build up on the flood basalt province. So this lower CO2 would have allowed ice growth past a critical latitude, and then the ice albedo effect would have caused runaway glaciation. There are some challenges to this fire and ice model, namely that other large igneous provinces in Earth history aren't associated with cooling and glaciation. Some of these were emplaced at higher latitudes and might not have had as big of an effect on planetary weatherability, but others were in place during warm background conditions. And recent modeling work by Minsky et al. Shows that snowball initiation via Franklin Large Igneous Province weathering is really only plausible from a cool background climate state. So in addition to the Franklin Large Igneous Province driving that final cooling, it's also been proposed that longer term weathering of these large igneous provinces throughout the Tonian cooled the climate and made it more susceptible to this final push. So in Svalbard, remember, we have an unconformity between below the Sturtian glaciation, but we can still use this record to investigate this longer record of lip weathering. So there is some evidence to support Tonian lip weathering. This mainly comes from radiogenic isotopes. So just to briefly remind you, osmium and strontium in seawater, or isotope compositions in seawater, primarily reflect the balance between a mafic mantle source, which is unradiogenic, low isotopic composition, and a radiogenic, or broadly more felsic, crustal source with high isotopic composition. And because these isotope systems are sensitive to composition, and because osmium and strontium both have long residence times and are well mixed in the ocean, we can use the isotopic signatures of these sediments, strontium, carbonates for strontium and organic rich sediments for osmium, to track changes in this global continental weathering flux through time. So for example, if a flood basalt province were erupted on land, the continental flux would become more unradiogenic or mafic, and so the seawater and resulting sediment would be reflected in a lower isotopic composition. And this is indeed what we see in the mid to late Tonian, a decreasing isotopic composition, which is consistent with mafic or lip weathering occurring at a global scale. On the other hand, in very simplistic terms, neodymium isotopes in sedimentary rocks are indicative of the source age of crustal material input into that specific sedimentary basin. So it's a local sediment provenance proxy. Mantle neodymium is depleted relative to samarium due to neodymium being slightly more incompatible and preferentially incorporated into the melt. So the mantle has a higher samarium neodymium ratio, and with time, the radiogenic daughter 143 neodymium accumulates, leading to this higher neodymium isotope composition of the mantle. Whereas continental crust is relatively neodymium enriched relative to samarium, a low samarium neodymium ratio, and evolves to have a lower neodymium isotope composition. And because of these isotope differences are so minute, we multiply them by 10,000 and use epsilon notation, comparing them to the chondritic uniform reservoir, sure. So it tends, essentially, when we're looking at graphs of epsilon neodymium, we're taking this, this top graph and rotating, so CHUR is at 0. And then you can see here that old crustal material would be characterized by very low epsilon values, and newly formed mantle material, such as lips, should have a very high epsilon value. And then we use the depositional age to correct epsilon values for the decay of samarium to neodymium that's occurring in the sediment after deposition to get this epsilon neodymium at depositional age. So that's what we're looking at here. I'm showing the neodymium isotope records for multiple Neoproterozoic sedimentary successions. And you can see that they're certainly higher than old continental crust, which I'm showing a very generalized field for here in purple. And these elevated values suggest that there is some input from younger or juvenile mantle-like material. One option for that mantle or that juvenile material is a lip source. I'm showing a composition for that here in this black line here. And indeed, previous neodymium isotope studies have attributed these relatively high neodymium isotope signatures to lip weathering. And this certainly might be the case for basins with proximal lip sources like Australia, South China, the Canadian Cordillera. But the neodymium isotope record from Svalbard, which I'm showing here in blue, has also been interpreted to support the fire and ice hypothesis, even though there's no known local lip source. However, juvenile or higher neodymium isotope signatures are also characteristic of newly formed felsic material, such as in material formed in an arc setting. So I'm showing here isotopic spread of arc rocks, and you can see that it's maybe more consistent with some of the neodymium isotope sedimentary data. Here I'm isolating the record from Svalbard and showing the generalized stratigraphy that it came from along the top. And we reinvestigated this record, adding almost all of the data points shown here and improving the age model, and importantly, adding these earlier Tonian data points to give these later values more context. And we did this to test whether this basin records evidence for lip weathering in support of the fire and ice hypothesis, or if instead these elevated isotopic signatures can be explained by weathering of juvenile felsic material. The neodymium values in these Tonian mudrocks are intermediate. They're higher than old crust, lower than juvenile mantle. And for the most part, these data overlap with measured values from the underlying Kappanstein group. So those are those volcanic and intrusive units that underlie the sediment. These data also indicate contribution from older crustal material when samples are pulled down to lower isotopic values. And then data from the Cryogenian and early Ediacaran show a shift towards consistently lower values, indicating a more consistent increased contribution from this old crustal source. You may also notice that there's potentially a slight increase in the youngest Tonian samples. These are from the Rosoya member. And it might look like this is evidence for lip weathering, but I do want to remind you that because of the hiatus in Svalbard, these were deposited about 10 million years before the onset of Franklin emplacement. And I'll talk about these samples separately later on, but for now I want to largely ignore them and talk about the broader trends in Tonian provenance. So these intermediate values indicate both a young and old crustal source to northeastern Svalbard during the Neoproterozoic. The young end member could certainly be a lip as proposed by previous studies, or as I'm showing here, the Kappanstein group. So these are rocks formed in an arc setting during the early Neoproterozoic. But how about this older end member? Looking at paleogeographically proximal locations, the nearby East Greenland basement, which I'm showing a field for in purple, is one potential option for this older source. But another option is the Grenville Sveconorwegian Province, which I'm showing on this map here in green. So this province formed through the continued arc collision against the southern margin of Laurentia, and then eventual continent-continent collision during the formation of Rodinia during the Mesoproterozoic. And because of that tectonic history, it comprises both young and old crust. And so the neodymium isotope values from the Grenville, which I'm showing in this broad green field, and the Sveconorwegian in this narrower, darker teal field, can really account for the entire range of neodymium values that we see in Svalbard mudrocks. And the big takeaway from all this is that all of these local or regional sources can explain the neodymium isotope composition of Svalbard mudrocks. And they're all really relatively felsic to intermediate in composition. So from neodymium isotopes alone, there's really no need to invoke mafic lip weathering as previous workers have done. But to differentiate between these sources of different lithology or composition, we need metrics that are sensitive to compositional variation and not just to source age like neodymium isotopes. And one way to do this is using major and trace element geochemistry. So the first indication that there's little influence from a mafic source in this sample set is that there's really no correlation between epsilon neodymium on the y-axis and trace element concentrations and ratios that are sensitive to lithology. So if there were a strong lip source in these sediments, you'd expect that samples with high or more juvenile epsilon neodymium would have high concentrations of trace elements that are more abundant in mafic material like scandium, vanadium, cobalt, chromium, also high titanium aluminum ratios and low thorium to scandium ratios. So except for these few samples that I'll come back to later on, again from the Rosoya member, we can see that there's really no evidence for a mafic source throughout most of this basin's history. You can also see this in rare earth element signatures of these mudrocks, which should be sensitive to source composition. These mudrocks have rare earth element profiles that are similar to post-Archean average shale, plotted here in red, which is to say they have composition similar to upper continental crust with high light to heavy rare earth element ratios. They also overlap with quite well with the underlying Kappanstein group. And they show really no indication from rare earth elements of a mafic source, which would be reflected in a flatter profile. And remarkably, you can see that there's quite little stratigraphic variation in these sedimentary units. So here I'm showing stratigraphic plots. These are immobile trace element ratios that are typically used to assess sediment provenance because they're not fractionated during weathering and transport processes. And again, you can see that in this 6 kilometers of sediment, there's remarkably little stratigraphic variation. And most samples have values that are typical of felsic to intermediate material. I'm showing upper continental crust fields here in these green lines. And data often overlap with values for the underlying Kappanstein group, which I'm showing in these pink diamonds. And then for reference here in purple, I'm showing ratios from the Franklin Large Igneous Province. I know that wasn't erupted till way up here, but I'm just showing it for a reference of what mafic material would look like in this space. You might again realize a few samples from the Rosoya member with trace element signatures more characteristic of a more mafic source, which I'll come back to in a few minutes. But one last thing I wanted to point out here, talking about these broader trends, is the effect of filtering on provenance interpretations. So you might have noticed that for the last few slides, I've had this asterisk down here stating that we've been looking at trace element data from a filtered mudrock data set. And here I'm showing the unfiltered version of this data set. Samples are colored by their calcium to aluminum ratios, which I'll show on the next slide, correlates well with their carbonate content. So you can see that samples with high calcium to aluminum ratios in orange and then red have a much wider spread than samples from our filtered data set plotted in blue. And they're actually often offset in the same direction as carbonates from the same stratigraphic unit. So those are plotted in gray. So this suggests that the geochemistry of these mudrock samples is controlled by carbonate contamination and not actually by sediment source. So they shouldn't be used to assess sediment provenance. And I point this out because if we had considered these samples, we might have interpreted this data set really differently. For example, these samples with low thorium to scandium ratios might have been taken as evidence for lip weathering increasing in the Akademikerbreen group later in the Tonian. Whereas really what this actually reflects is increasing carbonate content in mudrocks with the establishment of a carbonate platform in the Akademikerbreen group. So here I'm showing those calcium to aluminum ratios in mudrocks and how they correlate well with carbonate abundance. So this is from the subset of samples that we have both elemental and mineralogical data for. So we use this calcium to aluminum ratio of 0.2 to filter the rest of our mudrock samples. And that's where we start to see the effect of carbonate contamination on our trace element signatures. And it remarkably corresponds with a carbonate abundance as low as about 5%. Over here on the right, in these rare earth element plots, you can see that mudrocks with high calcium to aluminum ratios in red and orange have low rare earth element abundances relative to samples in the filtered data set. And they're much more similar concentration to carbonates, which are plotted over here in gray. The same trend that we see in the rare earth elements plots is true of other trace elements, that mudrocks with high calcium to aluminum ratios in red and orange often have low trace element abundances, and that's due to the dilution from carbonate phases, which have lower concentrations of these elements. And then it's also very clear in the major element geochemistry that samples with high calcium to aluminum ratios reflect carbonate content more than source provenance or chemistry. Samples with high calcium to aluminum have low silica and aluminum and high calcium and magnesium. And when these samples are filtered out, entirely different trends emerge between mudrock major oxides. So the takeaways from this are that it's clear that filtering mudrock data sets for carbonate content is necessary for determining sediment provenance, especially in mixed carbonate siliciclastic successions. Now I want to talk about these few samples from the late Tonian and Cryogenian, where there might actually be evidence for mafic provenance in Svalbard. The most juvenile neodymium isotope values in the succession come from the Convica member and the Rosoya member. These are samples from the latest Tonian, so they're stratigraphically closest to the Sturtian glacial deposits. And then I also want to highlight a few samples from the interglacial McDonald-Riggan member. These have elevated neodymium isotope compositions compared to other samples from the McDonald-Riggan member. Despite the high epsilon neodymium values, none of these Convica member samples plotted in yellow have any trace element evidence for a mafic source. However, the other samples that I'm showing here do. So on the right here, I'm plotting all the samples from this substurtian Rosoya member and from the McDonald-Riggan in squares. So samples from each of these formations that have the highest epsilon neodymium values, so around -2 for the Rosoya member and -6 for the McDonald-Riggan member, also have the highest molar proportion of iron and magnesium, so plotting to the right on this x-axis. They also have the lowest thorium to scandium ratios reflected in this lighter color on this top graph, as well as elevated vanadium and scandium ratios, so these warmer colors in the bottom two plots. And all of this is evidence to indicate a more mafic source for these 2 samples from the Rosoya member and 3 from the McDonald-Riggan member. But what is actually the source of this more mafic material? For the interglacial McDonald-Riggan member, it's likely that it could be an actual lip source, potentially eroding remnants of the Franklin Large Igneous Province after deglaciation. But for the Rosoya member, a lip source is unlikely. It was again deposited about 10 to 15 million years before the emplacement of the Franklin Large Igneous Province. And it's unlikely that there would suddenly be an increase in detritus coming from a very distal lip source in Northwest Canada if there's no evidence for that source through the rest of the underlying strata. Instead, I think these non-mafic but high epsilon neodymium samples from the underlying Convica member can provide some context for the Rosoya samples. The Convica member marks renewed extension with input of siliciclastic material into this carbonate-dominated succession. And the shift in epsilon to higher epsilon neodymium values may therefore provide some subtle geochemical evidence for basin reorganization and or new exposure of some of the local basement units. On the right here, I'm showing a plot of the Kaphanstein group chemistry, and you can see that some of the more mafic samples, really andesites in this case, from the Kaphanstein group have higher epsilon neodymium values and lower thorium scandium values. So it's a possibility that unsampled mafic units, which do exist from the Kaphanstein group, they just haven't been sampled for epsilon neodymium and trace elements, could have even higher epsilon neodymium and could be the source of these highest neodymium signatures in the Rosoya and Convica members. So a summary of what we talked about so far is that major and trace element chemistry from these mudrocks show no evidence for Tonian lip weathering, and that mudrock filtering is imperative for extracting reliable provenance and weathering data from these units. And finally, I want to talk about a more quantitative way to evaluate the contribution from potential sources and the possibility for minor lip contribution. And I'll do that with mixing models. So basically, we mix the composition of two sources, both their neodymium concentrations and their isotopic compositions, and modeled what sediments derived from this mixing should look like compositionally. So the results would be these black lines here. And then we compared that to the actual sedimentary data, which I'm showing in these kernel density plots in the background. But before talking about the results, I want to mention the sources that we chose to mix. So for a juvenile mafic member, we used neodymium isotope data and trace element data from the Gun Barrel Large Igneous Province that was emplaced around 780 MA in Northwest Canada. So it's the most proximal potential lip source to Svalbard during the mid to late Tonian. And then we compiled all the neodymium isotope data we could find from the Grenville Province from these many, many studies listed here. And for our old crust end member, we used the oldest cluster of data points with the lowest epsilon neodymium signature, which is shown here in blue. And then we use this same compilation for our juvenile felsic end member, which we just selected the more juvenile values from this compilation. And given that there was a really wide range in neodymium concentration, we actually modeled the juvenile felsic end member with two different options, a low and a high neodymium concentration. So these are the results from some different mixing scenarios. On this first graph, all the way at the bottom would be 100% old crust, 0% juvenile mafic material, and all the way at the top would be 100% juvenile mafic. So if these two sources contributed to Svalbard mudrocks, somewhere between 0 and around 60 or 70% mafic contribution would be needed to explain the sedimentary neodymium isotope data from Svalbard, which I'm showing again in that kernel density plot. Mixing of a juvenile mafic and a juvenile felsic end member really can't explain any of the sedimentary neodymium isotope data. However, mixing of a juvenile felsic and an old crustal end member can easily explain the entire range that we see here, especially when allowing for this range in the isotopic or in the concentration of neodymium in this juvenile felsic source. And then we also wanted to model a mixing scenario where we incorporated all three of these sources, and we did that by combining a 50-50 mixture of this juvenile felsic and old crust and then adding in the juvenile mafic as a second source. So there's really no way to explain any of the more evolved values, lower neodymium isotope values. But in this scenario, the more juvenile sedimentary data can be explained by around 0 to 40% juvenile mafic material. And what makes these mixing models more powerful and discerning is that we can actually take these mixing scenarios that explain the neodymium isotope data and model the resulting trace element ratios and compare them to actual sedimentary trace element data. So we take the mixing proportion of two sources that can explain the sedimentary neodymium isotope data and show that in this red region here on the x-axis as a proportion of juvenile mafic material. And then this mixing line shows the resulting trace element ratio from the mixing of these two sources. So where this line and this red area intersect is what the expected trace element ratio would be for mudrocks of this neodymium isotope composition in this mixing scenario. And we can see that we can then compare the actual trace element data from sedimentary units plotted here to this mixing scenario. And you can see that in this scenario, there's very little overlap between the predicted trace element ratios in yellow and the actual sedimentary data. So this means that this mixing scenario is only valid at extremely low proportion of juvenile mafic material. And even so, it can really only explain the lowest europium anomalies and the highest the lowest neodymium isotope values. However, scenarios in which the mixing lines do overlap with the sedimentary trace element data can explain both the neodymium isotopes and the trace element data of these mudrocks. So here I've plotted a few different immobile trace element ratios. And generally, we find that juvenile mafic plus old crust mixing scenario really can't explain the geochemical data of these sediments. But this juvenile felsic plus old crust mixing scenario can explain the range we see in both neodymium and trace elements pretty well. And then in this third scenario where we modeled the mixture of all three, the sedimentary trace element data can really only be explained by quite a low contribution of juvenile mafic material. So now what we've shown more quantitatively is that the geochemistry of these Neoproterozoic mudrocks in Svalbard can be explained by mixing of a juvenile felsic and old crustal source. And if it existed at all, the lip source really only contributed a very minor amount to these sediments. So before expanding back to the broader Neoproterozoic global context, I want to bring back this slide from the beginning just to remind everyone that we're not talking about whether the weathering of the Franklin Large Igneous Province drove that final descent into the Sturtian glaciation, because in Svalbard there's an unconformity, but we're talking about whether the weathering of lips throughout the Tonian cooled climate and made it more susceptible to this final push. So our reinterpretation of the neodymium isotope record from Svalbard means that previous support for the fire and ice hypothesis was overstated, but it doesn't actually mean that mafic weathering wasn't significant during the Tonian. Basins with more proximal lip sources should record evidence in neodymium isotope signatures if lip weathering was taking place during the Tonian. And then more broadly, I want to point out that our work also demonstrates that these elevated neodymium isotope signatures of sediment have non-unique interpretations and really have to be evaluated within the context of major and trace element data to differentiate between mafic and felsic juvenile sources. Such a data set doesn't yet exist or isn't published to fully evaluate the neodymium isotope record from Northwest Canada. The existing neodymium record, which I'm plotting here, is actually quite similar to that from Northeast Svalbard, with all of the Tonian mudrock data falling between -3 and -11, and then decreasing following the Sturtian glaciation. And based on detrital zircon studies, Neoproterozoic basins in Northwest Canada received a lot of sediment from the Grenville Province. And in fact, low-resolution neodymium isotope studies that yielded these elevated neodymium signatures that we see here were originally interpreted to reflect this Grenville source, similar to our interpretation of Svalbard. So given our findings in Svalbard, further geochemical data are really needed to establish what the source of this elevated neodymium isotope data is from Northwest Canada during the Tonian. Elevated neodymium isotope data coupled with high concentrations of mafic trace elements provides strong evidence for mafic contribution to Cryogenian mudrocks in Australia. These units were likely receiving detritus from local lip sources. However, the evidence for juvenile neodymium isotope signatures within the Tonian is much more limited. And determination of a Tonian lip source is complicated by the presence of older mafic units within the Musgrave block. And then the only location where I think there's really good evidence for mafic weathering occurring through much of the Tonian is from South China. So here, sedimentary neodymium values span +3 to -7. They're significantly more juvenile than basement, and they're also accompanied by high concentrations of mafic trace elements. So taken together, this Tonian record of lip weathering from detrital sediments is much more ambiguous than previously thought. However, there is still this evidence from osmium and strontium isotopes that I mentioned at the beginning of mid to late Tonian mafic weathering globally. So it's possible that mafic weathering in South China really dominated the global flux of osmium and strontium, and that lip weathering was globally significant at this time. But it's also been proposed by Yoon Park and others that these isotope signatures were caused by weathering of mafic lithologies within an arc setting, specifically from low latitude accretion events that were occurring in the Arabian-Nubian Shield at this time. So further work is needed to fully evaluate the relative role that lips and arcs played in cooling the late Tonian climate millions of years before the onset of Sturtian glaciation. And paleotemperature proxy data would be really useful in determining whether there even was a cool climate in the late Tonian. So at this point, I've gone through the main findings of this work and how they relate to reevaluating the role of lip weathering in the Neoproterozoic. But I do want to take another 2 minutes to touch on another finding that I think this community will find interesting. One thing that I haven't really mentioned is proxies for chemical weathering intensity, including mineralogy and chemical index of alteration, or CIA, which I'm showing in these box plots by formation here. And you can see that CIA values are similar to that of an average shale for most of the succession, spanning 65 to 85, most data between 70 and 80. And this is consistent with the clay mineral assemblage we see in these mudrocks, which contains illite, montmorillonite, iron and magnesium chloride, and even smectite. And you'll notice that cation-poor weathering products such as kaolinite or iron oxides that really only form during intense chemical leaching are noticeably absent, except in one formation, the Svanbergfjellet Formation. So samples from the Svanbergfjellet Formation also have the highest chemical index of alteration values, which is consistent with intense chemical leaching during weathering of the source region when this unit was deposited. Interestingly, the Svanbergfjellet also has the lowest epsilon neodymium values compared to its surrounding units. So it may reflect tapping of an older crustal source as the result of this extreme chemical weathering conditions. The Svanbergfjellet Formation is also unique for another reason. The 790 Ma Algal Dolomite, remember, of this formation has yielded really remarkably preserved organic micro and macro fossils, and it's considered to be a Neoproterozoic Lagerstätte. It hosts fossils like Proterozoic and Paleastrum that have been really important in documenting the Tonian diversification of eukaryotes. It's likely that this high kaolinite content and potentially the assemblage of other or of iron-rich clays preserved in this unit could have played a role in fossil preservation. Kaolinite is known to, or is documented in association with Burgess Shale type exceptional fossil preservation. And in 2020, Anderson et al. Reported that fossils from the Algal Dolomite member, shown here in red, are surrounded by these aluminum-rich halos, shown here in green, which likely represent kaolinite. Kaolinite is known to aid in the preservation of fossils due to its toxicity to microbial degraders, and it also promotes the transformation of organic remains into more decay-resistant compounds. But regardless of the exact mechanism, the occurrence of this exceptional fossil preservation in the algal dolomite member suggests a link to this unique intense chemical weathering recorded in this unit. So with that, I'll put back up my main conclusions here, and I'm happy to take any questions.
All right, excellent talk, Lexie. Thank you for sharing your work with us. We'll now open the floor for questions. Please feel free to use the raise your hand feature and I'll call on you in order, or you can type your question in the chat and I'll be happy to read it aloud. First hand up we have is Greg Vitalik, so feel free to go ahead.
Hi, Alexie. That was spectacular, and I agree with all of it, which is fantastic too. But first, a personal question: are you related to Kitty Millikin?
I'm not. I don't.
Not at
I don't
all.
think so. I mean, not that I know of, but
yeah, no, I know her well, and I really respect her work, which is kind of similar. But there's another explanation, of course, other than weathering, and that is just the evolution of life on land, which could have created this. And there's plenty of evidence for that. And the evidence not only comes from the fossils, and you've shown us a few already, particularly the vase fossils, which indicate a big step up in terrestrial productivity, because those are found in paleosols as well, but also from the paleosols themselves. And in fact, in Canada, there's been a focus on basalt weathering because Dick Holland years ago wanted to use paleosols as evidence of oxidation. And what he found was that felsic parent materials in paleosols were too insensitive to give him a good bead on what the oxygen levels were. And so he actually focused on basaltic paleosols back through time. And some of the famous ones are the Keweenawen and, we had several. But if you analyze the degree of weathering through time, it shows an increase in rate of weathering. I've published on this. In the same parent material, in the basalts, the weathering of the basalts increased through time, not because of the basalts, but because of something else, which I believe is the evolution of terrestrial weathering microbial ecosystems.
Very interesting. So you're suggesting that potentially cooling during the Tonian could have been linked to the evolution of land plants and increasing weatherability in that way?
Yes, the biological enhancement of weathering. I've had several papers about this. So even microbes are going to ramp up the CO2 in the soil itself on every lithology, basalt, everything on land. And that's what I think drives your strontium and osmium ratios as well. It's just a biological event of increased complexity. We have a lot more fungi. We have a lot more thecamebans in the late Tonian. There's an increase in uneven indications of multicellularity in the late Tonian fossils.
Yeah, very interesting. Yeah.
Yeah, so I love what you've done. The lip idea never struck me as all that great. Because why out lips? Right? They're basalts and they're very hard to weather. They're too dense. They don't give access to weathering fluids very well. And in fact, felsic tuffs and loose materials would be better if you want to make a purely lithological argument. But I think the argument is elsewhere. I think the argument is biological. Anyway, I'll get off my soapbox, and I really enjoyed that. Thank you very much.
Yeah, thank you.
Francis has his hand up.
Yeah, I've got a question instead of a statement. Really nice talk, Lexie. I really enjoyed that. you pointed towards felsic, juvenile felsic weathering as an input through the Tonian. And I was wondering if you could speak to how that relates to some of the tectonic models for the setting of the Tonian Basin. There's sort of two different models. One, it was accommodated by rifting, and the other is that it was accommodated by either dynamic subsidence or some bit of flexure due to a back arc or a retro arc setting with fringing arcs to the north. Is it possible your felsic, juvenile source could be from a fringing felsic arc?
Yeah, I mean, I think that unfortunately I think between like even intermediate and more felsic compositions, we can't get too specific identifying what the source is to these mud rocks, but I think in Svalbard we do have evidence for relatively felsic magmatism in the Kappanstein group. So the locally underlying units, as well as other relatively felsic magmatism in other sedimentary basins nearby during the Tonian. And detrital zircons, the few that we have from these sediments do reflect a few ages that are consistent with that source of that younger Tonian arc-like material. And sorry, I'm forgetting the other or the more broad
just a
part
question of whether
question.
it was consistent with a fringing arc and that being related to the subsidence rather than a rifted passive margin, which is commonly invoked for that setting of that basin.
Yeah. I think the other thing is we do certainly have in a lot of these sediments high zirconium concentrations. There is likely some amount of recycled material being input, but also a lot of this volcanic material does itself have pretty high zirconium concentrations, whether it's just being incorporated during crustal contamination. So I don't know that we can really distinguish between different tectonic models with these data, but I think it is consistent with the fringing arc model.
Thank you.
Yeah.
All right, we have a question from Jingjun, who simply asks, is the polar bear in the background from Svalbard?
It is. Luckily we were on the boat when we saw this polar bear, but did see some other polar bears while we were on land, which was a little freaky. But this is a polar bear on some of these Neoproterozoic carbonates here.
Paul, go ahead.
The absence of significant Tonian cooling is consistent with the absence of glacial deposits, with the possible exception of the Kona rock.
Mm-hmm. Sorry, was the question whether the absence of this cooling is consistent with that data or?
Well, I think it's not surprising because we've known for a long time that the Tonian generally has no glacial deposits.
Yeah, I think that's
so the cooling. If there was premonitory cooling before the Sturtian, it was not a long-lived cooling. It occurred in that 15 to 20 million years when there's no record in Svalbard.
Yeah, I think that's a good point that if cooling occurred, I think it's more likely to have occurred in this last 15 to 20 million years. And at least the record of basalt weathering shows that it was, potentially not a significant increased weatherability in the early Tonian.
Cenozoic cooling, which is as large as almost any cooling in the Phanerozoic, occurred in about 15 million years. At 50 million, mid-Eocene is one of the hottest periods that we know of, and yet we had a full-blown Antarctic glaciation by 34.
I mean, putting Paul's statement into a question, can your CIA data speak to that?
I think CIA data is especially, in this case, we don't have very high weathering intensity recorded in these units, except for that Svanbergfjellet Formation. But I think, CIA values are reflecting a pretty local weathering condition. So, for example, in the McDonald-Driggan and Dracoisan formations that directly overlie glacial units and should probably be reflecting really high CO2 concentrations in the atmosphere after deglaciation, have very low values. So that could just mean that locally physical weathering is outpacing chemical weathering. So I think maybe a much broader compilation of Tonian CIA values could speak to that, but I don't think from just this basin we can really say anything about temperature.
Well, glaciation tends to remove laterite. And so after a glaciation, you tend to have less weathered material.
All right. Next person with their hand up is Daryl Long. We can't hear you, Daryl.
Okay, my question is kind of old-fashioned. When you look at the petrography or the pebble counts in the glacial units, do they give you similar ratios to the ones you're speculating for your geochemical mix?
Sorry, the lithology of class within the glacial diamictites, are they consistent with the let me see if there's a good photo, or I can just go back to the beginning. The short answer is not really. The diamictite, the older Petrov-Breen diamictite, has largely carbonate class. I believe there are like two data points from epsilon neodymium from the diamictite matrix, which are more consistent with the later Cryogenian and Ediacaran data, but slightly higher. And then, that's actually from the Wilson-Breen. The Wilson-Breen does have a lot of extrabasinal class, but here, let me show the neodymium data from that. So the epsilon neodymium from the Wilson-Breen diamictite, the Marinone diamictite, is higher than the Cryogenian interglacial and early Ediacaran data. So that's likely because it's bringing in material just from a wider source region than the shales that were deposited in the interglacial and post-glacial time.
Okay, thank you.
The next person with their hand up joining us from Canada is Alex Kavalik. Please ask your question.
Oh, you're running something. Hey, Alexie, really cool talk. Thanks for that. I wanted to ask, you were correcting for some carbonate in some of this. So was that carbonate driving the epsilon neodymium values heavier or more mantle-like? I might have missed that.
I didn't talk about that. So we didn't actually filter our neodymium data set for calcium to aluminum ratios like we did for our trace element data. I have a plot here just showing that. So this is even a log plot. We didn't see that neodymium isotope or epsilon neodymium correlated with calcium to aluminum as much as like just trace element concentrations and ratios. So we didn't end up filtering that data set. Yeah.
Got it. Okay. Answer. Yeah, I was just wondering if there was like a clear difference between like the carbonate and the siliciclastics, because
I think carbonates,
you might expect it to trace it, or sorry.
Yeah, I mean, that was something I was considering, whether the neodymium or epsilon neodymium from more carbonate-rich phases would be higher isotopically, tracing more like global sources than the detrital sediment. I think ultimately most of these shales have, and we did really select mudrocks with high or low calcium to aluminum ratios for the most part. So I think the carbonate phase has such a lower concentration of neodymium that it's not affecting the values very significantly.
Yeah, it would be interesting to see if that would be a more juvenile source suggesting that there was maybe more global weathering of mafic material.
Yeah, there has been some work in Australia and suggested like doing preferential leaching experiments showing that exact thing. But those are mostly Cryogenian samples. Yeah.
Okay, cool. Thanks.
All right,
Yeah.
Andre?
Alexie, good talk. I'm just, if I understand correctly, you are suggesting that you could explain your samarium neodymium data by mixing of juvenile sort of Mesoproterozoic felsic volcanics and old basement. And so if that's correct, I'm wondering, I was expecting that at the end you would show detrital zircons data because they would talk exactly sort of to mixing between felsic volcanic rocks and old basement. And second, I was hoping you would actually do mixing calculations for sort of taking this Mesoproterozoic volcanics and old basement and trying to mix them and to reproduce your data. So I'm wondering if you have any comments on it.
Yeah, so so far there's very little published detrital zircon data from Northeast Svalbard that comes from that lower Veteranen Group, one sample. This is in Tianran Zhang's paper. So this top plot is detrital zircon from that, and then this is just like a compilation from one of Rob Rainbird's papers showing detrital zircons in a lot of these Neoproterozoic successions. So I know Justin Strauss has more detrital zircon data he's planning to publish from Svalbard, but that's not out yet. So I didn't really feel like I could comment on that. But yeah, I am suggesting that Mesoproterozoic or relatively felsic material, potentially from the Grenville province, is consistent with the neodymium data that we see in our mudrock samples. And I just have here a plot of neodymium isotope signatures of those Grenville rocks here that you can see are pretty consistent with what we see in our mudrock data when it's calculated for the time of sedimentation.
Thank you. The reason I ask is like we did some work in Greenland, and which is correlative succession, and you almost have no detrital zircons of sort of Neoproterozoic or polyproterozoic, Mesoproterozoic age until you get the very top of succession to the Ediacaran. So,
yeah, I know there is a big provenance shift that occurs, like a shift towards older detrital zircons in Svalbard, like consistent with our neodymium data that occurs kind of after the Sturtian glaciation. But yeah, I'm excited to compare the neodymium data to the final detrital zircon data once it's out there.
Yeah, it would be good. Thank you.
Yeah.
All right. If there are no more questions, let's give it up for Alexie one last time. And please join us next week for Carl Simpson and his talk, Theory, Experiment, and Fossil Record and the Origin of Early Evolution of Animals. So thank you very much, Alexie.
Thank you.